Good afternoon. I am going to talk about network traffic monitoring and, of course, packet capture. The main topics of today will be flows in the, NetFlow IPFix, security, of course, so to characterize the traffic with respect to network security, even though we are not security-oriented as Suricata. Big data, because if you have a lot of data, you cannot simply say, OK, I have the flow, I have the packet. You have also to solve the problem of using the data, because simply producing data is not very nice. And of course, 100 gigabit. Let me first say that it is 20 years that this original Ntop project, that was an open source only project, started. And through the years, we have developed a few things. Half of them, I would say, are open source. You can find them on GitHub. And some are proprietary, so are the software that allow us to live. And where is Napatech in this respect? Napatech has been one of the first vendor who has approached us, more than 10 years ago. It was probably Napatech was created 2-3 years before, and we use Napatech on this PF-Ring framework, and not natively. This morning we have seen some example of people using the NT API. We don't want to do that, because we believe that it is important not just to use a tool, but also to make it easy to use for everybody. This means that you can take all of our tools, run them on a laptop, low-end laptop, and then you can put an Napatech card, changing simply the device name, you can run your application, if the application is able to do so, at 100 gigabit without changing any single line of code. And also, we are supporting all the different Napatech API iterations, and therefore, you don't simply have to see what is happening underneath, because it's a problem of PF-Ring, it's a problem of Napatech. You simply have to benefit from the speed bump. Okay? So Ntop and Napatech are working together since a very long time. Now, let's move on. Packets. For many years, the word standard was enough. Okay? People were talking about SNMP, NetFlow, SFlow, and so on. So just the buzzword was enough. But unfortunately, this was not a good idea, because the innovation was stopped by those vendors. But today, 10 years ago, I would say, with the advent of virtualization of many computers, people that wanted to focus on results rather than on buzzwords, pushed a little bit towards a different direction, fortunately. So it is important to produce data in a way that you can consume the data. In the past, it was XML. Today, it's probably JSON. It is not important how you produce the data. If you have a proprietary format, such as NetFlow, it is a problem to translate from this format to a format that is open. So if you have Hadoop, such a big platform, you want to inject data regardless of the source. I think that Splunk did a good idea, a good thing many years ago when they put on this platform logs, flows, packets, everything. So this is where we are today. But we need to move from packet to flows and to activities. Flows are a way to compress information, because packets are good, but they are too many. They take too much space. So we have to compress them. Compress doesn't mean to gzip them. It means that we have to create a sort of summary that is meaningful for us, that is not really too raw. So it's something that we can search. It's something we can insert on a database. It's not a binary thing that we have to put on a database. So therefore, a flow is a good way also to save space, because packets take a lot of space. You know how much space you need for a 10 gigabit interface that takes more than 1.2 gigabytes per second. So we cannot really afford to save long-term data in a raw format, unless you have a system such as the one described before this presentation. And now we have the problem of visibility. We don't want to simply account packet and bytes, because we need to say more. We need also to spot, and machine learning is an interesting technology, I would say, to spot the flows that are more relevant than others, to understand in this big word what are the flows that mean something special, that indicate that there's a problem, indicate that there is something that we should focus on. And also, some metrics, such as, for instance, the top something, are interesting, but sometimes the problem is not there. In the past, we have seen that big attacks were mostly volumetric attacks or were attacks that were easy to spot. I mean, even looking at byte and packet, you simply look at a time series, you see a peak, you say, wait a minute, there is something special here. I want to analyze that. But this is no longer the case. Zero-day attacks or other type of attacks are very sophisticated. So you don't have to look at one metric. Actually, you have to go beyond this. So we have seen in the suricata presentation before that every flow has many attributes, okay? And this is what we have to do. So for instance, we have to provide metadata for protocols, such as decode the HTTPS certificate to say this is the host you are accessing, or the DNS query, and to add things like the response code or the latency, the application and the network latency to respond to that data, and to understand if your level of performance is still good or it is different from what you have expected. So simply don't look at just a time series on the screen, but try to move forward to the next level. Now, flow generation. So for years, people have used routers or physical devices to do so. But unfortunately, those devices are still not very interoperable between the model and the vendors. If you think about Cisco, for instance, even inside the Cisco company, there are different models. And Cisco ESA is a good example. The flows they produce are called flows, but they are somehow special in content. And they change from one model to another. There are tiny differences that make them hard to analyze. So therefore, we see that there is a problem, and that this is the problem we try to solve. If we use those devices, first of all, we have to pay a ticket to the vendor, not just in terms of price, but also in terms of evolution, because we cannot do more than what they are providing us. If they are providing just bytes and packet, and that's it, we have to survive with those counters. We want to do more, and we want to create something that can produce good analytics. And in order to do that, we must have new, or let's say extended metadata in addition to what we have seen for years. For this reason, we have decided, also pushed by our users, that it was important to create more interesting, more meaningful metrics. Because without metrics, you cannot do much. If you read the papers, you will see that there are many papers talking about, okay, is this encrypted traffic real SSH? Long discussion, evaluation, results. But at the end, we must be sure that what we are saying is actually what has passed on the network. We cannot simply say, maybe this is the percentage of accuracy. So we have to be sure, because if we have to report a problem, it must be so. So this means that the 5 tuples, IP source and destination, port, source and destination, protocol, and some simple byte-on-packet counters are not enough. And unfortunately, this is what you receive even today from a NetFlow-enabled router. So we need something more. We need something like latency, packet drops, retransmission, quality, anything that is necessary to create and to pinpoint a specific problem without going into the percentage of accuracy of something. We must be sure that if this is a flow about DNS, and if DNS response is not what we expect, then there is a problem. If those responses are too slow for a very long time, then we have to act. We have to do something. We cannot simply work, and pretend that all we have to do is what those vendors are providing us. So therefore, for a very long time, we have said to ourselves, okay, this is what we believe, but what people want, is this their need? Are they willing to put physical probes or sensors, if you want to call them sensors, in the network instead of relying on routers? And fortunately, even with Napatech, we have approached some customers. The answer is yes. People want to have visibility. Sometimes it is required by the law to see everything. But in general, we see that with packet sampling or with other techniques for reducing the size of the data set, you are losing the important data. You don't see enough with respect to what you have in mind. And if you lose packets, if you have drops, you see that you have a problem. You cannot reconstruct the flow of communication. And therefore, we need to fill this gap. We need to say, OK, the vendors are not able to provide us what the market wants. We have to find a solution. We have to create something different that can fill this niche. So therefore, we have said that we want to generate rich monitoring data regardless of the speed. If the speed is a problem, we have to find a solution for that. But we cannot simply say we want to monitor 1 or 10 gigabit and not above 10 gigabit because we have a problem. We want to be able also to generate rich monitoring data because sometimes we say, OK, we need too many CPU cycles. So therefore, we are not able to produce everything we would like. So we have to reduce our data set by using sampling or using other techniques. No, we cannot do that. We need to create something that is able to give the visibility we need at the speed of the network. So if today the speed is 100 gigabit, we have to do it at 100 gigabit. We have to find a solution. And the speed is always increasing. I'm not telling you something new today. So 10 gigabit is kind of commodity. Probably it's a little bit outdated. If you buy a server today, you will probably find 10, 25 Ethernet adapters. So 100 gigabit is here today. Is not coming. It is here. So we have to be prepared to higher speed. So we need to be able to have, same as we did with PF3, an answer to the same problem regardless of the speed. We must be able to provide rich monitoring data that we see at 1 gigabit because we have CPU cycles available at 100 gigabit. And we have to find a solution for that. We cannot rely too much on the CPU performance because the performance is increasing, but it's not increasing as much as we would like because if we look at the CPU frequency compared to the network speed, we see that they are diverging. So we have to leverage on this. So we have to exploit multi-core architecture. And of course, we have to be able to handle 100 gigabit in a proper way because if we waste all the CPU cycles simply to capture packet, we won't have time for doing anything else. The transition to 100 gigabit is happening. Actually, for many users, it has already happened. And 40 gigabit, that was the target speed for a very long time, is now 100G. So it means that we have to provide a solution to this new speed in a way that allow people to say, OK, if I move to 100 gigabit, I will now be able to monitor the network as I'm used to do it today at 10G. Because otherwise, this transition can be problematic if you lose completely visibility at higher speed, and people don't want that. When you want to move to 100G, you have various solutions. One solution is, for instance, is to scale inside the server. So in essence, using this technique called RSS, you can distribute the traffic across the cores, the CPU cores, and split the load across cores and maximize the performance of your system. But we need to be able to capture 100 gigabit. This is the problem. And if you want to have a solution at the network level, you can use OpenFlow programmable switches to split your traffic. But because those devices are static, so you must know in advance what to filter, how to drop, how to distribute the traffic, and this is not always possible because the traffic is changing. So in essence, we need to be able to be prepared to receive from one link a full 100 gigabit flow of packets and be able to handle it. We cannot simply use this sort of tricks to reduce a high-speed problem to a lower-speed problem and put more servers, because sometimes this is not possible. Actually, usually, this is not possible. So therefore, in our transition, we need to take into account that there are also low cost compared to FPGAs ASIC-based NICs, such as the Intel Red Rock Canyon or Cento, but they don't provide 100 gigabit. So when we talk about 100 gigabit today, I talk about 100 gigabit line rate, 140-something million packets per second. I'm not talking about the 100 gigabit link that you plug on the server, and then you see only 20 gigabit of traffic. I'm talking about the line rate here. So therefore, the only solution here is to use an FPGA, is to use a solution such as the one we have used and we have found with Napatech, because there are no other solutions available on the market. And it is also important to understand that capturing traffic is expensive. It is not free. So you need to make sure that you have enough CPU cycles for analyzing the traffic, because if you spend or if you burn a lot of your memory bandwidth simply moving the packets because you are using a solution that is not effective, then you don't have CPU cycles for doing the rest. This is very important. It's not important just to count packets. Sometimes I see benchmark and I say, I'm able to capture so many packets per second. And then you look at the benchmarking code, and you will see that they are simply counting packets. When I say monitor traffic, I mean move the whole packet to memory and go inside the packet payload and either dump it to disk or do DPI on it. This is the message. I'm not talking about counting packets, because counting packets is not what I want to do. I want to do, like I explained before, a deep analysis of the traffic. This is very important. So people are used to do things like capture, filter, traffic monitoring. The needs are very different from one person to another. But in essence, there is also another problem that everybody has, the fact that you want to have a compact solution, a device that is really compact in space, that can do all those things at a higher speed, saving rack space. Because if I give you a solution that takes, a rack for doing 100 gigabit, I don't know if I've really solved the problem, besides the hardware cost. I don't think I have. So we must be able to create small and compact devices. We have started with commodity hardware. We have started 20 years ago saying that we don't want to go with proprietary things. We want to be as open as possible. And this is still what we are doing today. So we want to be able to take a server, a Dell, an HP, whatever you can buy, put a network adapter, put some software, Linux as operating system, and that's it. This is the goal. And for 100 gigabits, I told you, or even for 40 gigabit, packet capture is not the only problem. We need more than that. So when you have to evaluate a network adapter, you also have to look at the other features that might be not too important on the brochure, but are very important when you develop an application, such as, for instance, how to distribute traffic to multiple applications, how do you combine ports together in hardware and then redistribute this traffic in a coherent way to applications. These are features that are very, very important. So in essence, what we want to do is to solve this simple problem. Is it possible to create an Intel-based box able to do 100 gigabit flow monitoring? This is the idea. In particular, one unit, that would be the best. But is it possible also to provide visibility? So not just byte and counters from one IP to another, but much more than that. Metadata, DPI, this type of things. And in particular, using low-cost hardware, so hardware you can buy on the market. Because of that, because we have been involved with Napatech in a project for a large customer, we have decided to take this challenge and to try to provide a positive solution to that. And together, we have created a solution that is based on a software we have developed that is named Cento, where Cento means 100. Centum is a Latin word for 100. We want to do not simple NetFlow, but we want to do advanced NetFlow, DPI, and metadata information. The architecture of this application is this. It's a bit complicated if you want. Okay, first of all, we have to merge incoming traffic because people often at this speed use network tabs. And this is something that is done in hardware by the Napatech card. Once we have received the traffic, we also have to program the card to distribute the traffic across multiple cores. And Cento is able to spread on various cores the processing tasks and do what we want. So in essence, to provide net flow information. Here we have created something called micro NDPI. NDPI, if you go back to the first slide, is an open source DPI toolkit we maintain. Here we use either the full-fledged DPI or a micro version of that. In this version, we support only SSL, HTTP, DNS, and all the sub-protocols. So for instance, when I say Facebook, for me, is SSL that is going to Facebook. And we can do real-time traffic monitoring. So we can see this is our open source web monitoring application. We can see what is happening in real time because Cento is creating flows and sending flows, is streaming them to Ntop and G. Or we can dump packet to disk. Of course, at this speed, it is not possible to dump 100 gigabit to disk. Even dumping 100 gigabit to disk alone will be too much. But what is the idea here? The idea is to combine security with visibility. Here we want to see what is happening on our network. And we also want to send specific traffic to tools like Suricata, for instance, that you have seen before. And when Suricata makes a decision that thinks that a certain machine is compromised or whatever, through a REST interface, we receive a command that says, OK, the packet you are receiving should also be sent to disk. And note that here, we are writing packets and metadata. What is metadata? Not just the 5-tuple, but also the DPI information. So in essence, I want to go on the pickup, say, give me all the BitTorrent traffic that my PC did, okay? Something that is not port or IP-based. This is the idea. So more slowly. This is the use case of traffic monitoring. So you will see, you take Cento, you take the NIC, and then you can generate the traffic and send either flows out to a collector or send them in text or JSON format to those type of systems. We support 0MQ and Kafka, so you can publish this data to a big data system and you can import them on those systems. There's another mode that allows to use it in line, okay? Or for instance, in this case, to use it before the packet to disk application. So in essence, we create flows out of everything, and out of them, specific packet will be discarded. The other one will go to disk. Again, this is instructable through the REST API I told you before. Or is it possible to use it in this other mode, where you can take the NIC, capture the traffic, and distribute the traffic to the IDSs, and the IDSs can send a feedback back to Cento so that we can change the configuration. Now, the flow format that we support is NetFlow v5, v9, and EpiFix. We have decided not to have very configurable template, but we have only a few options because we want to go fast. Because one of the problems here is that if we add flexibility, the code will be full of if, then, if, and these are breaking the performance. So we want to go fast. We want to go line rate. In addition to the basic information element, we export things like the application protocol, the minor and the major protocol, latency information, so network application latency, and metadata that, for instance, include the URL, the certificate, or the response code. Now, for the packet inspection, we don't use any specific toolkit, but we have developed our own that is called NDPI, and we use that. The performance impact of DPI is only on the first packet of the flow because we have to do DPI at the beginning of the flow. So usually it's one packet for UDP or a few packets, usually 10, including the three-way and shaking for TCP. The performance can be affected, therefore, not only in terms of packet, but in terms of flows, because we have to do this activity for every flow. So usually it can be reduced by 20 or 40% in the worst case. But if you want to have visibility of most popular protocols, micro DPI has a performance degradation that is almost unnoticeable. So it is really up to you to decide, based on the performance level that you have in mind, what to expect. Of course, because here we are talking about flows, I cannot simply talk about packet per second, because if I send you the same packet over and over, it is very easy, because DPI happens only once at the beginning of this conversation. Whereas the more flows, the heavier is the load on the DPI component. So it is really important to consider these things into the equation. Now, instead of reporting you a super server doing NetFlow with Cento, I want to take this use case. This use case is coming from a real user. It's a research network in Europe, and they have 100 gigabit links. They are using the Ntop card. For various reasons, they wanted to save money, because, of course, they are not super rich. And so one day they told me, we bought this motherboard. That is it's a very small motherboard. I have a picture here. Okay, this is the motherboard you can find also on Amazon. It costs not too much. Okay. And they said we want to save money. This is a macro ITX board, so it's a small board. It's nothing like a rackable server. So they said we want to be able to do 100 gigabit here. So help us to optimize the code. So we have used the Ntop NT208. That is the newest generation. So it has two times 100. So you can do merging on the card, 100 gigabit. And then they have 1 gigabit card for exporting traffic. The total cost, not including the Ntop card, of the hardware, so motherboard, case, memory, everything, is below $3,000 US. So this is the card, and this is the CPU. Okay, again, it's not a super fast CPU. It's the D series Xeon processor. So this to give you an idea of the speed. Using synthetic traffic, they have a traffic generator. It's possible to do almost 100 gigabit, but again, packets are very big. Okay, they probably don't represent what you have on the network. You have only 12 physical cores, but testing with 25 new flows per second per core, okay, we are able to do that. But then it was surprising to me when they moved this from their lab to a real network with real traffic. So in essence, they have put this one at the edge, so not on the data center. Okay, talking about the edge of 100 gigabit network is probably not a good term, but in general, what they did is that they didn't put it in the center because they didn't want to put tabs and everything in the center, but they put it. They have various locations across the country, and they wanted to create a very cheap, monitoring box. So in essence, with this cheap box that costs less than $3,000 US, they are able to monitor their own network using the Ntop card. So what is the message here? The message is that it is possible to do that, and not to do this with an Intel server, but also using a low-end server. But, of course, we have a problem on performance. Because if we also want to save packet to disk at the same time, we cannot for sure dump 100 gigabit to disk, because people, first of all, we don't need that. But they also want to save only those packets that are relevant. So we have made some tests, and we have seen that the main problem here is the memory bandwidth. So hardware, the FPGA per se, is able to do many things, but then if we have to monitor flows and send packet to an Egress, then honestly, we cannot go above 20 gigabit line rate. So 100 gigabit is analyzed, and 20 gigabit can be saved to disk at the same time because of the memory bandwidth limitation. But for these people, this is not a big deal because they don't want to save everything to disk. They want to receive flows in real time to understand where are the problems. And in case there is a problem with a compromised machine, they will tell Cento to dump to disk those packets. So therefore, we are good. This as long as we are below 20 gigabit or even better, in their case, 10 gigabit because of the machine. But now, we have flows, we have speed, but we have to look at them. Because people are used to a paradigm like Gmail, okay? So in Gmail, the most interesting thing, I think, when it was introduced, was the fact that you have almost unlimited storage. In those days, everybody was giving you a bit of this space, and this guy said, OK, put everything here. It will stay here forever. And this is the same thing that people have in mind for everything, in particular for packet to disk or for flow to disk. They would like to have an appliance that can save everything forever. You simply forget it at some point. In case you need a certain packet, you go and you find it. Unfortunately, it is a bit more complicated than that. So therefore, people started to talk about big data, whatever big data means. I don't know. There are several definitions of that. But the only thing I can tell you is that, for me, big data means, for sure, a lot of hardware and human cost to maintain it, and a lot of expertise to keep it running. It means that for sure. Because you have a cluster, you have machines, you have to talk to them, you have the complexity. Okay, you're trying to solve one problem, but at the same time, you're creating another problem, if you want to say that. So in essence, they are able to store your flows, even at high speed, but at the same time, okay, they have limitation. Not all of them, but most of them are not real time. So it means that you cannot send one flow to the big data system, but you have to send a few of them. So it means that you're adding latency. It means that you are not able to do query in real time, only on historical traffic, whatever historical means. That might mean maybe 10 minutes ago or 1 hour ago. So no real-time visibility, and this is a big limitation. And then are distributed by nature. So you need nodes, you need people, and you have to pay attention also to the failure. Because if you have a lot of hardware can break, and software can break. So you have a complexity. So you're trying to solve one problem, adding complexity. So as we said before, we wanted to create an Intel-based system able to do 100 gigabit. But now, we have another problem. So we don't know what to do with this data, because this data is too much. And having a big data system is a solution. Our user that is using the Cento is very happy with a big data system. But this is a huge customer that don't have problems operating such a cluster, because he has people, data center. Not everybody has that. I told you the example of the research network before. These people are moving to 100 gigabit because 100 gigabit is here today, but they don't have the expertise to run the system at such a high speed. So we want to combine visibility and capacity and query speed. So we want to be able to create a self-contained solution, so ideally 1 unit rack, where it is also possible not just to look at the traffic in a big data system that is far away, but inside the same box. Because a problem of big data is that sometimes people don't like it, because if the network goes down, you are not able to reach the big data system anymore, exactly when you have to save your important data into it. So to make this long story short, we said we want to create into this single box also the possibility of dumping flows to disk in a way that can be indexed and retrieved in real time without a big data system. Big data, it will be on top of it. So if you want to have a multi-node deployment, it is possible to do it. But today, we want to be able to see what is possible to do on a single node. For this reason, it is more than 1 year, almost 2 years, that we are trying to find a solution to this problem. And the first thing we did was to create something based on a technology called compressed bitmap index. So we want to create an index of your data in a compressed format that allows us to search as fast as possible. We have a packet-to-disk solution similar to what Napatech has to the Pendium, and there we have an index. But when we have created this technology 5-7 years ago, we didn't have much time. The CPU were a little bit slower than today. And the only thing we would be able to do was to create a digest. I wouldn't call it index. So a sort of reduced amount of data where we can do a sort of a semi-linear scan. So because this is a little data compared to the pickup, it will be faster. But I cannot call it index. Instead, today we want to create a real index. We want to be able to say, I want to jump exactly to this packet, to this flow, and want to retrieve it. In particular, if you have a distributed system, each node should be able to do that. And like I said before, if you use Cento, you will have packet and flows and metadata. And we want to do this on a single box. So why we have created this bitmap? Because all the bitmap systems we have been able to find were optimized for other problem domains and were not optimized for networking. Just to make you an example, if you want to compress data, if you want to compress networking data, you must know that the protocol ID is not an 8-bit integer, but it's usually, most of the time, TCP, UDP, ICMP, sometimes something else. So if you want to compress it, you cannot treat this as an 8-bit number. It is something special. The same for the time. The time is not a 32-bit integer, but it's a time with certain properties. If you read, for instance, the Gorilla paper from Facebook, you will see that for time series, they are using a compression algorithm that exploits this property. So in essence, we have decided to create something optimized only for networking that is not designed for replacing a database, but is designed for indexing this data we are producing. Now, the challenge here is not indexing flows. The challenge is indexing packets, because at 100 gigabit, we have noticed that in average, we are generating 50,000 flows per second. That at the end makes 4 billion flows a day. Billion. Okay, this can be a big number, but it's nothing. Because if you think in terms of packets, at 10 gigabit, you will have almost 50 million packets per second. And because a day has 86K seconds, you will see that this is much more than that. So the data set we have is very big. We cannot expect to solve this problem with an SQL database, let's say. We have to create something different. So we want to be able to combine this solution with what I've shown you before. And how can we do that? So I want to show you some preliminary results that we are able to achieve using this bitmap index. So indexing, I'm talking about 10 gigabit because I told you that when we dump traffic to disk with Cento, we have decided that we won't exceed this 10 gigabit because at about 20 G, we have problem with the memory bandwidth that will be not able to go above this. Of course, you can decide to have only packet to disk, only flows to disk, but here I'm talking about both at the same time. So if you create an index-based IP source, IP destination, the file where you have, so the pickup file ID, and the offset of this packet in a file. This one is good for answering to queries like, this machine has been compromised. I want to have all the pickup of this machine from Monday to Tuesday, or the pickup of two machines that are talking together. So when we do this, we are able to index packet to disk, you see, in about 60 nanoseconds. Because at 10 gigabit we receive, in theory, when packets are small, 64 bytes, a packet every 67 nanoseconds, we are able to do indexing while capturing at line rate 10G. If we had other fields, like for instance the port, so if we want to search the port or the protocol, we need a little bit more than that. So it means that we need 2 threads to do that, because this is about, in average, below 120 nanoseconds. So it is really possible to do all this at the same time. Yes, it is possible to create an index. But now you're wondering how fast you can search. What I forgot to say is that the index is compressed, so it's very small. I'm not talking about the data. So we are putting them on an NVMe drives. Because they take very little space, it is really possible to search and to index at the same time without too many problems. So this is an example of a query that we ran out of 4.4 billion records. As you can see, searching for a specific IP, it is pretty fast, 200-something milliseconds. And this is another example. So out of so many records, so in essence 350 gigabytes of pickup, this query that you can run on TCP dump, so doing a linear scan, will take, let's say, 8 minutes. With our indexing system, will take about 1 second. So what I want to say this, just to wrap up. Napatech, for us, has been an enabler, because it was not possible for us to implement this type of things without this technology. There is no discussion. Maybe we can do it at 10 gigabit, but definitely not above that. not just because of the packet capture, but because of the way packets will go to memory. If packet will go to memory without prefetch, without being ready to be analyzed, then we'll be able to see the number when we are counting the packets, but we'll not be able to see the performance when we'll be able to dump. We need to dump this packet to disk, or we need to do the packet inspection. We have demonstrated that, and this customer, this joint customer is very happy, that it's possible to do 100 gigabit monitoring. And I told you that also with a commodity server that costs less than $3,000, it is possible to do 100 gigabit today on a real network with real traffic. We try to also to say we want to give also the possibility of creating on the same box an index that allows you to search data. And this is possible. And I show you some preliminary results of our technology that we'll introduce soon. But again, the indexing system, it's already on GitHub, all in one box. So I want to say today that the dream that we had to be able to create a single box, flows, plus packets, plus indexing, it is now possible. If you have questions, I'm here to answer. Thank you.
Say what I asked earlier, 100 gig, like how just the physical deployments of 100 gig networks are there? How do you see the demand driving? You see a lot of deployments of that on top of
this is something we have done. We have started to create 3 years ago. At the beginning, it was something just for one customer, for one large customer. Also because the technology at 100 gigabit, the optics, was not really stable. So in essence, there were a few standards, things were moving. But today, we see that if you have to create a network, you prefer to spend a little bit more money and to create it at 100 gigabit rather than to rely on technologies that might not be, let's say, the best for a specific use case. So for instance, last week I was talking with an ISP in Milan. And they said, OK, we don't need 100 gigabit today. For us, 10 or 40 will be enough. But we decided to jump to 100 gigabit because 100 gigabit will guarantee, this is the idea, lower prices. It will become commodity, even though it's partially commodity today. When I say commodity, it means that you are able to analyze this traffic in case you have a problem, so to troubleshoot with a PC at a reasonable cost. So we're not talking about $100,000 just to analyze one link. So I see that people are telling us this story over and over. So I don't consider 100 gigabit for everybody. But I believe that compared to 3 years ago when we have started this project, it's kind of standard. I mean, people are used to know the speed. They can find the network adapters on the market. So routers prices, I'm talking about the 100 gig ports, are falling a little bit. The cost of optics are also more reasonable than what it has been. So I think that 100 gigabit, for those people that are not yet using it, will come pretty soon. And if they have to make an investment, they say that they will jump on this technology rather than to use 4TG, for instance.
So obviously there's no like standard Intel network chipset for 100 gig right now.
No, there is. It's called.
Like you're going to Red Rock Canyon or something.
Yeah, but I mean, it's not a solution for this type of.
Yeah, that's not. Have you looked at other things other than FPGAs as a way to?
Yeah, it was one of the first slides that I told you. There are some, for instance, Chelsea or Miricom. There are a few companies, but those cards are not designed for network monitoring. They are designed for other tasks. They are designed, for instance, for storage. So they are not an option for this type of problems. Because, for instance, at the beginning of this conference, you talk about the Intel Fortville. This card is designed for data center, for virtual machines. It's not designed for receiving packets in order from one stream. It is designed for putting as many virtual machines as you can on this box. So you have to create many links to them. that at the end is not what we want, because it means that if we exploit the CPU cores this way, we'll end up shuffling the traffic. We don't see the timestamp anymore. I mean, they are for different use cases. So, I mean, if you look at the brochure, you will read 100 gigabit or 40G. But at the end, they are not suitable for this type of problems. Not even for security, because they will have probably the same problem we have here. Okay. Okay.
Thank you very much.
Thank you.